Decision trees from start to finish in Python. We're gonna do it today. Hip, hip, hooray. StatQuest. Hooray. Well, thank you guys very much for joining me for my webinar in decision trees from start to finish in Python. I'm going to share the screen right here. Can you guys all see that? I'm sharing the this Jupyter notebook. I hope everyone can see it. Yes, I got a yes. That's great. So what we're going to go through today is this Jupyter notebook, and I'm going to email you, every single one of you guys, a copy of this. It will include the Jupyter notebook, which has to be opened up within Jupyter, but also a copy that can be run directly in Python. So if you don't have Jupyter installed on your computer, but you have Python, you still should be able to run everything that we talk about. And all of the writing in here, there's lots of writing, lots of comments. All of that will be in comments in the code. So you will get everything one way or the other. Yeah, so today we're going to use scikit-learn and cost complexity pruning to build this classification tree right here, which uses continuous and categorical data from the UCI machine learning repository to predict whether or not a patient has heart disease. Note, all these things are hyperlinks. So if you want to learn more about the UCI machine learning repository, or you want to learn more about the specific data set we're using, you can click on the links and learn more. So there are lots of hyperlinks in here. Anyways, classification trees are an exceptionally useful machine learning method when you need to know how the decisions are being made. For example, if you have to justify the predictions to your boss, classification trees are a good method because each step in the decision-making process is easy to understand. Now, I know classification trees, some people think they're not the sexiest of machine learning methods out there, but they are super practical and are actually very frequently used in the medical profession because the decisions, you can trace exactly what the rationale is for everything. And that's important in certain fields. And so, and I also like them just for like exploring data in terms of like looking to see which features or variables are the most important. So there's a lot of cool things we can do with decision trees. And so we're going to learn all about them. So we're going to learn about importing data, which is not very exciting, but it's important. We're going to talk about how to deal with missing data, identifying it, dealing with it. We're going to talk about formatting the data for decision trees. Specifically, we're going to talk about one-hot encoding. We're also going to build a preliminary classification tree, and it's going to not be very good, but then we're going to optimize that thing using cost complexity pruning. And then once we've optimized it, we're going to build, draw, interpret, and evaluate the final classification tree. And this all covers a lot of material, so we're going to move pretty quickly. However, if you have questions at the end of each section, feel free to bring them up. You can also, you should all have my email, the statquest.bam@gmail.com. You can email me questions later. So with that, let's just dive right in. Oh, by the way, once you get this code, I strongly encourage you to play around with it. Playing with the code is the best way to learn from it. And I've got alternative ways to do things in the comments. So you can try like the way we're going to do it today, but you can also try alternative versions and see if you get the same results or not. Okay. So someone just asked if we're going to share this notebook link. I'm going to actually email everyone this notebook. Everyone's going to get a copy of it, plus all the code. So you'll get everything. Um, so don't worry about if I move fast and you're having trouble taking notes or something like that. Don't worry about it. You're going to get everything. And I've commented and written everything up uh, uh, with lots and lots of details, some of which we'll cover today. And there's actually stuff we won't get to, so you can read more and learn more once you get the notebook. Okay, so the very first thing we do is load in a bunch of Python modules. Python itself, as many of you may know, but some of you might not, just gives us a basic programming language. These modules give us extra functionality to import the data, clean it up, and format it, and then build, evaluate, and draw the classification tree. Note, I'm doing everything in Python 3, and if you've got your own installation of Python going, you're going to need certain versions of, of the modules. These are listed here. And I've got a little blurb on how to update modules should you need to do that. But since I don't have to do that, we're just going to skip right here. And these are the modules we're going to load. We're going to load pandas. We're going to do that for manipulating data and for one-hot encoding. We're loading NumPy to calculate the mean and standard deviation. And then we're importing matplotlib to draw some graphs, and then a bunch of scikit-learn modules and bits to do classification trees and confusion matrices and cross-validation. So with a Jupyter Notebook, some of you guys may know this, some of you may not. If you want to run code, you just click in the pane that has the code and it gets highlighted. And then you can go up here and you can click that play button and it'll run everything. There's also key combinations for doing the same thing, or you can go to the run menu. So we could do Control Enter to run this selected cell, or we could click here. When we do, you will see a star show up here, and that means Python is working. And when it's done working, it'll put a number there. The actual number is not very important, so don't worry about that. But when you try to run this, you may see a little star for a little bit, but when the star turns into a number, you should be good to go. So we've imported the modules. So now we're ready to move on to the next thing. We're going to import the data. We're going to load in a data set from the UCI machine learning repository. Specifically, we're going to use the heart disease data set. And this data set will allow us to predict if someone has a heart disease based on their sex, age, blood pressure, and a bunch of other metrics. So we're going to use pandas to read that data frame in. And when it does, it returns a data frame, which is a lot like a spreadsheet. The data are organized in rows and columns, and each row can contain a mixture of text and columns. And the standard variable name for a data frame is the initials DF for data frame. So that's what we're going to use here. We're going to try to stick to the Python conventions. So we've got this code, and we've got data frame. That's going to be our new data, DF. That's going to be our data frame. It's our new variable. And we're setting it to the data we're going to read in using read CSV, which is a pandas function. The data is, I'm also going to email you the data. It's a relatively small file, so you'll get the data as well. However, as you see below, we can also read it directly from the machine learning repository by just plugging in the URL for the data. So I'm going to run this code. Bam. Okay, now we've got the data loaded into a data frame called DF, and we're going to look at the first 5 rows using the head function. So we've got df.head, and that will print out the first 5 rows. I'm going to use Control Enter, and that prints that out. By the way, different computers. I've got a Macintosh that I'm using right now. If you're on Windows or a PC or Linux, it may be a different key combination to run the code. Just go up to the run menu and figure out what it is on your platform of choice. All right, so we see the first 6 rows, they're kind of a mess. We got row numbers and column numbers. However, we do not have column names. And since nice column names would make it easier to know how to format the data, we're going to replace the column numbers with the following column names. I got these names, by the way, off the UCI website, so I didn't just make them up. We've got age, sex, chest pain, resting blood pressure, cholesterol, fasting blood sugar, resting electrocardiographic results, this maximum heart rate achieved, exercise-induced angina, um, and a bunch of other things. The point is, we're going to set the column names with df.columns, and they're going to be set to this array of column names. And then once we've set the column names, we're going to print out the first 5 rows like we just did. And hopefully we'll see nice, pretty looking column names. So let's run this. Bam. Okay. So now instead of column numbers, we've got nice column names, which are much easier to remember and manipulate. Okay. So now that we've got the data in our data frame and we've got nice column names, we are ready to identify with missing data. Identify and deal with missing data. I apologize. So I've broken this into 2 parts. The first part is going to focus on identifying missing data, and then the second part's going to be focused on dealing with missing data. And unfortunately, the biggest part of any data analysis project is making sure that the data is correctly formatted and fixing it when it is not. The first part of this process is identifying and dealing with missing data. Missing data is simply a blank space or a surrogate value like NA that indicates that we failed to collect data for one of the features. For example, if we forgot to ask someone's age or forgot to write it down, then we would have a blank space in the data set for that person's age. There are 2 main ways to deal with missing data. One is just to remove, if it's a single column or row that has a lot of missing data, we can remove that row of data or we can remove that column. Alternatively, we can impute the values that are missing. And in this context, impute is just a fancy way of saying we can make an educated guess about what the value should be. So if we were missing a value for age, instead of throwing out that entire row of data, we might fill in a missing value with the average age or the median, or use some more sophisticated approach to guess an appropriate value. So first, what we're going to do is we're going to see what kind of data we have in our data frame. And we'll do that with the D types by looking at D types. So we've got dataframe.dtypes. And we run that, and that tells us that age is a float, which is good because age is supposed to be a number. Sex is a float. Maybe that's good, maybe that's not. So we got a bunch of floats. And then we've got CA and FAL both have the object data type, and one column, HD, which is just short for heart disease, whether or not someone has heart disease, is an integer. So the fact that the CA and FAL columns have object data types suggests that there's something funny going on in them. Object data types are used when there's a mixture of things, like a mixture of numbers and letters. And in theory, both CA and FAL should just have a few values representing different categories. And I know this from the UCI website. So you can, if you want to learn more about this data set, I've actually got more about the data set further down in, but you can also read about it on the UCI website. Anyways, so what we're going to do to investigate what's going on in these columns is we're going to print out their unique values. So we're going to start with CA. So we've got data frame, and then in square brackets and single quotes, we've identified the column we are interested in. We're interested in the CA column, and we're interested in seeing the unique values. So we're going to use the unique function to print out those values. So we run it, and we see that CA contains numbers 0, 3, 2, and 1, and question marks. The numbers represent the number of blood vessels that were lit up during fluoroscopy, which is some sort of diagnostic procedure. I actually don't know the details about it. It's not super important to be able to follow along with what's going on in this webinar. And the question marks, however, those represent missing data. Now we're going to look at the unique values in the column called THAL, which is short for thallium heart scan. And we're doing the exact same code that we had before. We've got the data frame, and in square brackets and single quotes, we specify which column we are interested in looking at, and then we print out the unique values. And again, we see that THAL contains a mixture of numbers representing the different diagnoses for the thallium heart scan and question marks, which represent missing values. So now that we've identified some missing values, we need to deal with them. And that leads us to missing data part 2, dealing with missing data. Since scikit-learn's classification trees do not support data sets with missing values, we need to figure out what to do with these question marks. We can either delete these patients from the training data set or impute the missing data, or impute values for the missing data. So first, we're going to see how many rows contain missing values. We do that, we're going to count the number of rows. So we're going to use the len, which is short for length, function. And we're specifying with this line, we want to look at rows in the data frame, the location of which this is true. So is there a question mark for the CA value, or that's a pipe, which represents a logical or a bitwise or we want the rows that have a question mark in the thal spot. So we're going to run this code, and we see that there are only 6 rows that have missing values. And since that's not very many, we're just going to print them out. So we're going to run the exact same code we just ran. However, we're not going to wrap it in the length function or the len function. So we're not going to count the number of rows. We're just going to print them out. So let's run that. Here we are. We can see a question mark here in the thal column, a question mark here, blah, blah, blah. We've got these question marks. So that's what the data looks like with the question marks. Now we're going to see how many rows are in the full data set. So we're using that length function again, only this time we're not specifying which rows we want to look at. We're just saying, let's count all of the rows. And when we do that, we see we've got 303 rows. And so 6 of the 303 rows, or 2%, contain missing values. And since 297 is still plenty of data, relatively speaking, to build this classification tree, we're going to remove the rows with missing values rather than try to impute their values. Note, imputing missing values is a big topic that we will tackle in another webinar, because there's lots of ways to do it. There's lots of nuance. And so that's real high on my to-do list for what the next webinar is going to be. So by taking the easy route, by just deleting the rows with missing values, we can stay focused on what we want to talk about today, which are decision trees, because we still have a lot to talk about with decision trees. So what we're going to do is we're going to remove the rows with missing values by selecting all of the rows that do not contain question marks in either the CA or thal columns. So this looks very similar to the code we were just running when we wanted to print out the rows. However, instead of looking for rows that have the question mark, we're looking for rows that do not. So that not equal says do not match a question mark. And we want to do that for both of these columns. And we want to use the logical and to get all of the rows that do not have a question mark here or here. We want everything but those rows. So we'll run that. Oh, by the way, we saved the results in a new variable called df no missing. So this is our data frame with no missing values. And since DF no missing has 6 fewer rows than the original data frame, it should have 297 rows. We can verify that with this command. And we see that we got it. The math works out. So hooray, the math works out. However, we can also make sure that CA no longer contains question marks for printing its unique values. So this is just like what we did before, only this time we're calling on DF no missing instead of just DF alone. And we see that we just have numbers and there's no question mark here. So that's good. And now we're going to do the same thing for thal. And again, we see we just have the numbers. So bam, we have verified that data frame no missing, or the data frame with no missing values, does not contain any missing values. Note, CA and thal still have the object data type. That's okay. Now we're ready to format the data for making a classification tree. All right, the first thing we need to do when we format the data for a classification tree is split the data into 2 parts. We want to have the columns of data that we will use to make classifications, and we want the one column of data that we want to predict with the data over here. And we're going to use the conventional notation of capital X to represent the columns that we will use to make the classifications and predictions, and lowercase y to represent the thing we want to predict. In this case, we want to predict HD, the column specified by HD, which is short for heart disease. And the reason why we deal with missing data before we split it into X and Y is that if we need to remove rows, splitting afterwards ensures that each row in X will correctly correspond to a row in Y. If we do it the other way around, everything's going to get mixed up. So what we're going to do is we're going to copy all of the rows, all of the columns, except for the one column that is named HD. And I've got some alternative ways to do this code, so you can play around with it once you get the Jupyter Notebook. And then what we're going to do is once we copy everything but HD, we're going to look at the first 5 rows just to verify that we did it correctly. So there we go, and we see on the right side where we no longer have that column called HD, so that worked out well. And now we're going to just copy the HD column into our new variable called Y. Hooray! Okay, now that we've created X, which has the data we want to use to make predictions, and Y, which has the data we want to predict, we are ready to continue formatting X so that it is suitable for making a decision tree. All right, here we get to the fun part, one-hot encoding. A lot of you people may already know what one-hot encoding is. If you don't worry. This is something we're going to go into in detail. Now we have to split the data frame into, now that we have split the data frame into 2 pieces, X, which contains the data we want to use to make classifications, and Y, which contains the known classifications in our training data set, we need to take a closer look at the variables in X. The list below tells us what each variable represents and the type of data, float or categorical, it should contain. Okay, so we've got age, which should be a float because that can be any number, and we've got sex. That should be a category. That should be a value of either 0 for females and 1 for males. We have chest pain, which should also be a category. We've got 4 different categories. We'll go through those categories in more detail later. But we see in this list, we've got resting blood pressure. That's just a number, so we're going to save that as a float. Serum cholesterol, that's also just a number, so that's a float. And then we've got categories, and different things like that. Uh, However, just to review, let's go look at the data types in X to remember how Python is seeing the data. So this is how the data should be considered as some things are floats and some things are categories. But when we go to XD types or X.D types and we see what data type each column has, we see that a lot of these things that are supposed to be categories are like slope is supposed to be a category, but we have it stored as a float. Okay, so there's a problem with that. However, before we get to that problem, I'm going to say that we see that age, resting blood pressure, cholesterol, and the latch are all float 64, which is good because we want them to be floating point numbers. That's the way the data is supposed to be. All of the other columns, however, need to be inspected to make sure that they only contain reasonable values, and some of them need to change. This is because while scikit-learn decision trees natively supports continuous data, like resting blood pressure and maximum heart rate, they do not natively support categorical data like chest pain, which contains 4 different categories. Thus, in order to use categorical data with scikit-learn decision trees, we have to use a trick that converts a column with categorical data into multiple columns of binary values. And this trick is called one-hot encoding. Okay, at this point, you may be wondering, what's wrong with treating categorical data like continuous data? And to answer that question, we're going to look at an example. For the CP chest pain column, we have 4 options. 1, typical angina. 2, atypical angina. 3, non-anginal pain. And 4, asymptomatic. Now, if we treated these values 1, 2, 3, and 4 like continuous data, then we would assume that 4, which means asymptomatic, is more similar to 3, which means non-anginal pain, than it is to 1 or 2, which are other types of chest pain. That means the decision tree would be more likely to cluster the patients with 4s and 3s together than patients with 4s and 1s together. In contrast, if we treat these numbers like categorical data, then we treat each one as a separate category that is no more or less similar to any of the other categories. Thus, the likelihood of clustering patients with 4s and 3s is the same as clustering 4s and 1s, and that approach is more reasonable, partly because I don't really know what this means. Are 1 and 2 more similar? I don't know because I don't know. I'm going to use one-hot encoding to force scikit-learn to treat this like categorical data rather than uh, uh, continuous data. So now let's inspect and, if needed, convert the columns that contain categorical and integer data into the correct data types. We'll start with the chest pain by inspecting its unique values. Okay, so the good news is that chest pain only contains the values it is supposed to contain, 1, 2, 3, and 4. So we'll convert it using one-hot encoding into a series of columns that only contain 0s and 1s. Note, I've got a long description on the different ways to do one-hot encoding. There's 2 major methods. One is called column transformer from scikit-learn, and the other is called get dummies from pandas. Both methods have pros and cons. We're going to use get dummies today because I think it's the best way to teach how to do one-hot encoding. I think it by far is the best way to teach it. However, column transformer is more commonly used in production systems. So make sure you're familiar with both. And one way to do that is just read this write-up that I've provided you. It provides you with all the pros and cons of the different methods. So at your leisure, you can go through that. However, so we're just gonna use get dummies. because I think it's better for teaching. Um, so what we're going to do is we're going to start with chest pain. And just to see what happens when we convert chest pain, we're going to do this without saving the results, just so we can see how get dummies works. So what we're doing is we're going to use this Panda function, get dummies, and we're passing it our data frame, which we're calling X. That's the data we're using to make prediction, and we're specifying one column. We're just going to specify the chest pain column. We could specify a bunch of columns and convert them all at once, but right now we're just going to specify chest pain, and we're going to print out the first 5 rows to see what it does to the chest pain column. So let's run that. And we can see in the printout above that Get Dummies puts all of the columns it does not process in front, and it puts chest pain at the end right here. So everything we did not touch is up here on the left side, and everything that we did touch was with just chest pain is on the right side. It also splits chest pain into 4 columns, just like we expected it to do. Chest pain 1.0 is 1 for any patient that scored a 1 for chest pain and 0 for all other patients. Chest pain 2.0 is 1 for every patient that scored 2 for chest pain and 0 for all other patients. Likewise, we have chest pain 3 and chest pain 4, and this accounts for all 4 different options we had for chest pain. So now that we see how Get Dummies works, we're going to use it on the 4 categorical columns that have more than 2 categories, and we're going to save the result this time. We're not just going to print it out. Okay, note, in a real situation and not a tutorial like this, what you should do is verify that all 5 of these columns only contain the accepted categories. I feel like every data set I've ever worked with always has someone just typing in something completely random. And we need to get rid of that stuff. So use that unique function to make sure that each one of these columns is correctly formatted. However, for this tutorial, I've already done that, so we're going to skip that step. So here, we're doing the exact same thing we did before, except now we're specifying 4 columns to process. And then when we're saving it in a new data frame called X encoded, and then we're going to print out the first 5 rows of X encoded. Bam, there it is. So we've got chest pain, resting electrocardiogram, we've got slope, and we've got foul. And so they've all been one-hot encoded. Now we need to talk about the 3 categorical columns that only contain 0s and 1s: sex, fasting blood sugar, and exercise-induced angina. As we can see, one-hot encoding converts a column with more than 2 categories, like chest pain, into multiple columns of 0s and 1s. Since sex, fasting blood sugar, and exercise-induced angina only have 2 categories to begin with and only contain 0s and 1s, we do not have to do anything special to them. So we're done formatting the data for the classification tree. Hooray! Note, again, in practice, we would use unique to verify that they only contain 0s and 1s, but to save times, just trust me. Now, one last thing before we build a classification tree. We have Y, and that's what we're trying to predict. And it doesn't just contain 0s and 1s. Instead, it has 5 different levels of heart disease. 0 for no heart disease, and 1 through 4 for various degrees of heart disease. We can see this with the unique function, so y.unique, bam. So we see that we've got all these different values in the Y column. However, in this tutorial, we're just going to make a tree that does simple classification and only care if someone has heart disease or not. So we're going to convert all numbers greater than 0 to 1. And the way we're going to do that is we're going to store the indices of every time this statement is true. Every time the value in y is greater than 0, we're going to save that index. And then we're going to set all of those indexes to 1, or all the values at those indexes to 1. And then we're going to verify that we only have zeros and ones. So we're going to run this code, bam, and we did it. Actually, that's a double bam. We finally finished formatting the data for making a classification tree. And now over here in the chat, I see there's a question. Naomi Thompson asks, is there a limit to the number of types of chest pain to make sense to use in one-hot encoding? Is one method better than other when one has hundreds of classifying values? It depends. If all of those hundreds of classifying values are unique categories in and of themselves, then yes, we need to use one-hot encoding. And that could happen if we have a massive data set. If we've got hundreds and hundreds of categories for a single variable, we'd have to have a huge data set, and that can happen. And yeah, so we would apply one-hot encoding, and we would then end up with this data frame. Our X encoded data frame would then have hundreds and hundreds of extra columns added to it. I've never used a data set like that before in scikit-learn, so I cannot guarantee that it will not cause the machine to crash. However, there are machine learning methods like XGBoost that are designed to deal with situations like that specifically. So that's another webinar that we'll do in the next couple of months. I've actually already got the Jupyter Notebook ready for XGBoost. So I'm actually, just a sneak preview, next month we're doing support vector machines, and then we're going to do the following month we're going to do XGBoost, and then I think after that we're going to do imputing data, imputing missing values, and going through all of the various ways for doing that. So that's a little shameless self-promotion right there. Now let's move on and build a preliminary classification tree. This is preliminary because there are lots and lots of, actually, someone just raised a hand. So before we get too into this, I'll go back and address this. If we use dummy variables, don't we run the risk of perfect collinearity among dummies? If yes, how do we deal with them? As you saw, I guess it is possible to get collinearity among the variables. The nice thing is with regression trees is they are relatively immune to that as a problem. Typically what regression trees do is they order the columns alphabetically or numerically. There's some way it goes through the variables, and it just picks the first one that it gets to. And if I've got multiple columns that have the exact same data, and that first column is really good for classifying, and so it does a great job separating, and the other columns would do just as well. It just uses that first one every time. So it ends up not being an issue if we have redundancy in our data set. And that's one of the nice things about decision trees. All right. So I think we are ready to move on. All right. So we're going to build a preliminary classification tree. This is a classification tree that is not optimized. That's why it's preliminary. Then we'll go through how to optimize it once we get this going. So the first thing we're going to do is we're going to split our data into testing and training data subsets. So we've got X underscore train, X underscore test, Y underscore train, Y underscore test. And we're using train test split to take X encoded and Y and split them into training and testing pieces. And I've set the random state to 42 so that when you run this code, you will get the exact same results that I get. After we split the data, we're initializing a decision tree classifier, and then we are going to fit the data to the training data. And so let's run this. And it's uneventful because we didn't print anything out and we didn't draw anything. However, this piece of code will draw the decision tree that we just created. It's a huge tree. I'm using the plot tree function that comes with scikit-learn. And we just pass it the tree that we created and trained, the classification decision tree. And we've got a few parameters that we're passing it to make it easier to look at. So let's draw this. There it is. This is a monster decision tree. It's a lot bigger than the tree I showed you at the very top of this Jupyter Notebook. I also, by the way, I see some people are raising their hands. I'll get to those questions once we're done with the section. We're almost done. Okay, so we've built this classification tree, this monster. We're going to see how, and so far it's only seen the training data set. So we're going to see how it performs on the testing data set by running the testing data set down the tree and then drawing a confusion matrix. And we're going to do that with this function called plot confusion matrix, and we pass it the tree that we've created plus the testing data sets. And we're going to add labels so the confusion matrix is easy to look at. So let's run that. And there is our confusion matrix. Okay, so we see that of the 42 people that did not have heart disease, 31 of them, or 71%, are correctly classified. And of the 33 people that have heart disease, 26 or 79% were correctly classified. So the question is, can we do better? One thing that might be holding this classification tree back is that it may have overfit the training data set. So we're going to prune the tree. Pruning, in theory, should solve the overfitting problem and give us better results. Okay, so we finished that section. I'm going to look and see at some questions. I know some people raise their hand. And we've got some stuff in the Q&A real quick. Yes, someone asked about whether I'm going to answer this live. Someone asked if train test split is 70-30. I believe that is the default. So right here, when we're running train test split, we're just using the default splitting, and I believe that's a 70-30. Someone asked why I say this is a huge tree. And the reason why I say it's a huge tree is actually I know what the final tree, the best optimal tree is. We actually looked at it at the very beginning, and it's much, much smaller. So this tree may be huge, maybe not huge. It's relative to the optimal tree that does the best job with the testing data set. In this case, I know that it's huge. And how do I know it's overfit? I guess I know because I've already optimized the tree, and I've seen that it performs much better, and the much smaller ones performs better. So in general, when you're doing machine learning, that's a big step you need to do. You need to you make a preliminary tree, just like we did. Make your confusion matrix, and then try to optimize it. Because this confusion matrix is sort of a base. Can we improve on that? If we can, then we know that original tree was overfit. But we also know that by setting parameters and trying to optimize it, we actually improved things. So this is sort of our base, ground base that we're starting from, and we're going to try to do better than this. Someone asked if this was production code, would we use scikit-learn or would we use something else? I think scikit-learn is fine. I mean, it just sort of depends on the situation. If you've got tons and tons of data and need a lot of optimization for a massive data set, um, scikit-learn is not great for that. But for relatively small data sets like what we're using, sure, go ahead and use it. It's fine. I've answered. I hope I've answered these questions. I see one in the chat that says, "What happens if we remove the missing values after splitting the data into testing and training?" Um, uh, it depends. If you're going to remove rows of data, try to do it beforehand because you don't want a severe imbalance. If we, say like we have got testing data set and most of the uh, uh, rows that we're going to remove are in the testing data set, we'll do, the testing data set will shrink and things will get out of balance. So that's something you need to be aware of if you want to wait. I'd recommend just getting it over with earlier on. However, imputing values is another story. If we want to impute values, it's best to do that after splitting and testing. And so that's something we'll talk about when we talk about in the webinar for imputing values. Okay, I think I've addressed everyone's question, and I think we're ready to move on to cost complexity pruning. Decision trees are notorious for being overfit to the training data set. And there are a lot of parameters like maximum depth or the minimum number of samples. Like decision trees have lots of parameters that we can set, and they're all designed to reduce overfitting. However, pruning a tree with cost complexity pruning can simplify the whole process of finding a smaller tree that improves the accuracy with the training data or the testing data set. So that's what we're going to do here. And it's going to allow us to skip having to deal with a lot of these sort of tedious parameters, because pruning with cost complexity pruner just takes care of them all in one fell swoop. Pruning a decision tree is all about finding the right value for the pruning parameter alpha, which controls how little or how much pruning happens. One way to find the optimal value for alpha is to plot the accuracy of the tree as a function of different values. We do this for both the training data set and the testing data set. So first, we're going to extract the different values for alpha that are available for this tree and build a prune tree for each value for alpha. Note, I'm omitting the maximum value for alpha because that just leaves us the root of the tree, and we don't want to use that. So I'm going to run this code. We are running a little bit behind schedule. So I'm going to breeze through this by just telling you that this is how this chunk of code, which you'll get, so you don't have to memorize it, but this is how we extract the values for alpha. CCP stands for cost complexity pruning. So these are the cost complexity pruning alphas. And here's when we're peeling off the maximum value for alpha, and we're not going to use that. And here is where we're going to create an array of decision trees, and we're going to use a for loop for each value for alpha. We're going to create a decision tree, and we're going to see how it performs. And we already did that. Now we're going to graph the accuracy of the trees using the training data set and the testing data set as functions of alpha. All this code is doing right here is it's drawing this graph. So the blue is the accuracy for our training data set, and the orange is the accuracy for the testing data set. You can see that with the full size tree, when alpha equals 0 and we have the full size tree, we do the best with the training data set, but we do not do very well with the testing data set. And we see that as we prune, we increase alpha. So as we increase alpha, the size of the trees gets smaller. And as the trees get smaller, our testing accuracy improves. And that's good. That means we can prune the tree and we can actually perform better with the testing data. And just by looking at this, we can kind of guess that a good value for alpha is 0.016. Note, I don't know if you guys watched the cost complexity pruning video with StatQuest. In that, we are pruning a regression tree, and that the score, or we evaluate that tree with the sum of the squared residuals. When we evaluate a decision tree, we're using Gini, and Gini values range from 0 to 1, and so these values for alphas are way smaller than the ones that are in the StatQuest on pruning. But there's a reason for that, because Gini values only go from 0 to 1, and they don't, whereas the sum of squared residuals can be this huge number. Okay, now what we're going to do, now that we've seen how to use cross-complexity pruning to improve the accuracy, we're actually going to use cross-validation. So before, in this section, we just used the way the data was split between training and testing, that original split. But we only used one split. We didn't use tenfold cross-validation to validate that that wasn't actually optimal across all of the different ways we could subdivide the data. So now we're going to use cross-validation. This first bit of code is going to use cross-validation to show that if we just eyeball this number without using cross-validation, if we don't use cross-validation and we just pick the first number we get, we actually don't get the optimal tree. We get it at one point, but we see that another splitting of training and testing data set, another fold, gives us really bad accuracy. And so we want to avoid that. And that's just a function of how the data was split. So we're using cross-validation to make sure that we don't get tricked. Okay, so the graph above shows that using different training and data sets with the same alpha resulted in different accuracies, suggesting that alpha is sensitive to the data sets. So instead of picking a single training data set and a single testing data set, we're going to use cross-validation to find the optimal value for cost complexity pruning alpha. So here we're doing the exact same thing we did before. However, now we're calculating the accuracy with cross-validation for each value for alpha. And then we're going to plot a graph of the accuracy. Let's run that. And here we see, using cross-validation, that overall, instead of using, this is the value we've been using before, 0.016, this value to the left might be better overall over the each fold of cross-validation. So instead of setting CCP alpha to 0.016, we need to set it something closer to 0.014. So we're going to find the exact value by sort of narrowing down the range that we're looking at between 0.014 and 0.015. And here's that value for alpha. And we're going to store that in a new variable. So we've got a new variable called ideal cost complexity pruning alpha, and that stores it there. However, at this point, Python thinks that this variable that we just created, ideal cost complexity pruning alpha, is a series, which is a type of array. We can tell that because when we printed it out, we got two bits of stuff. The first was 20 right here, which is the index in the series. And the second one is the value for alpha. We need to convert this to a float before we pass it to a classification tree. So that's what we're going to do. And we do that just by asking for alpha. So hooray. Now we have the ideal value for alpha, and we can build, evaluate, and draw the final classification tree. Okay, now we're on the last section, but before, there's a couple of questions I want to answer real quickly. Someone asked if the alpha value can be found with grid search. Yes, definitely. Grid search is a way of looking at different parameters, or trying different values with different values at different values with different parameters at the same time, as it basically it tries all different combinations. See, we've got a bunch of questions in the Q&A. Um, uh, is there a mini method to find the intersection from the graph instead of guessing it? I'm sure there is. I'm blanking on it right now. Um, uh, where is Stack Exchange when we need it? I would just Google that on Stack Exchange. I'm sure there's something good. And someone asked, can we just do cross validation from the get go? And the answer is yes. There's no need to do it the way I did it, where I just kind of did it simply and then use cross validation. Basically, I was just trying to emphasize why we do cross validation, to show that we'll actually get a different value once we use it. Is single cross validation sufficient for model evaluation, or is nested cross validation better? I'll be honest, I don't know the answer to that question. So I will say that's another Stack Exchange question. Okay, so moving on, we got just a few minutes. I'm shooting for 12:05 as the optimal finish time. Since we started 5 minutes late, let's end 5 minutes late and we'll be on time. If you have to leave early, don't worry. You'll get a link to this video, to this webinar. You'll be able to watch it again, and you'll get this Jupyter notebook so you can go through it at your own pace later. Okay, now that we have the ideal value for alpha, we can build the final classification tree by setting this parameter, CCP alpha, to the ideal value. So that's what we do. We use the exact same call that we did before. However, this time we're setting this parameter, and then we are fitting it to the training data set. And now what we're doing is we're plotting a confusion matrix, but now we're using the pruned tree. Hooray! The pruned tree is better at classifying patients than the full-sized tree. Of the 42 people that did not have heart disease, now we're up to 81% correctly classified. Before, we only got 74%. And for the people with heart disease, we're up to 85%. And before, we only had 79%. So now we're ready for the last thing, which is to draw the prune tree and discuss how to interpret it. So we're going to draw the tree. And this is the prune tree. Now, just for reference, this was the original tree, which is huge. And after pruning it, we got down to this, and this little guy performs better than that big tree does. And it's because that big tree overfits the data of the training data. It fits it like a glove. And someone, I recently read somewhere, I wish I could remember where I read it, but someone said that overfitting is sort of like memorizing all the answers to an exam, rather than understanding what the questions actually are. So by pruning it, we're forcing the tree to not memorize the answers, but to do a better job classifying. So we're going to discuss how to interpret the tree. So each node in the tree has a column name that was used to split. So we used CA. Values less than 0.5 go to the left. Values greater. So if this statement is false, we go to the right. We've got the Gini and purity for the node, the number of samples in the node, and the number of classifications in that node. So we've got 118 people that do not have heart disease, and 104 people that do have heart disease. And lastly, the class tells us whatever category has the majority. And so since no heart disease has the majority, the class is no heart disease. It's also colored according to whoever has the majority. So all of these orange or orangish nodes have a majority of no heart disease, and the bluish nodes have a majority of yes heart disease. The darker the color, the lower the Gini impurity. So the better the split, the better uh, the the sort of bias towards one category or the other. So this guy has a relatively low Gini impurity, especially compared to where we started, where there was almost a 50-50 split between people with heart disease and without heart disease. But by the time we get down here, we've got an extreme bias towards people without heart disease after looking at CA, the thallium heart scan, old peak, and then getting to this leaf. The leafs, by the way, don't have column names because they're no longer splitting the data. So, in conclusion, we have imported data, identified and dealt with missing data, formatted the data for a decision tree using one-hot encoding, built a preliminary decision tree for classification, and that's what we use as a reference to know if pruning or optimizing the tree was going to make any difference. Then we pruned with cost complexity pruning. Then we built, drew, interpreted, and evaluated the final classification tree. So hooray! Triple bam, we made it. Oh, a couple things before we go. I want to say a lot of people, when they register, they'll use one email to register with Zoom and another email because that's their PayPal account, or another email associated with the payment. When I email this out, I will email it out. Make sure you check both because I get a bunch of lists of emails and I can't make sense of which one is the one you check the most often. So if you have multiple email addresses, make sure you check both. What else do I need to notice? The video and this Jupyter Notebook should be available by tomorrow at the latest. Somebody asked for views on a C4.5 tree. And I'm going to be honest and say, I don't actually know. What we've gone through is CART, and I can't remember the difference between CART and C4.5 right now. I will say that CART uses Gini. We could have used entropy, and actually I created, I used entropy. I did just earlier this morning, I was like, hey, I wonder what will happen if I use entropy instead of Gini. And so shocking to me is that the tree performed much worse. I was under the impression that entropy and Gini were this roughly equivalent and that you could just use them interchangeably. It turns out that at least with this data set, that is not the case. Anyways, I want to. Someone asked me to confirm a recommendation for using a production system as an alternative to scikit-learn. I unfortunately do not have an opinion on that. I wish I did, and that's something I'll look into and hopefully have an answer for you guys later. I'll try to, if there's questions I've given super lame answers to, I will try to research and send answers as part of the email that I send out to people. Someone asked if there's a way to know which features have the most influence. Yes. Yes, there is. You can just look at the tree to get a sense of which parameters were useful. You can also look at drop in Gini scores. We can print all this stuff out. All these values that we're looking at, we can actually store those in variables and then parse algorithmically. So we could see which variables are associated with the greatest drop in Gini. And so that's a way we could figure out which variables are the most influential or the most important for separation. All right, everyone. Thank you very much. I really appreciate you for joining the discussion, and I'll try to address any other questions in the email if I don't get them to them right now. Thank you very much. Uh, it really means a lot to me that you're here, and I hope everyone is safe. And we'll talk to you. I guess in the next live stream or the next webinar next month. We're doing support vector machines. So there you go. Oh, someone did ask if decision trees are better for medical data than random forests, and I don't know. I love random forests. I'm a random forest dude. I'm always thinking about them. I think it might be appropriate in a medical setting. It just sort of depends. I would like for it to be, because I like random forests. But in terms of like sheer interpretability, simplicity, decision trees are the best. Random forests are similar, but still a little more challenging to interpret. So that's the answer to that. All right. I hope everyone's doing okay. Until next time, quest on.